kid. He's like, oh, that's so cool. He's gonna watch every sport, every outdoor thing he's gonna watch, but he'll never go. It's not good.
Okay, we'll wait a little bit. Maybe let some other people come in if they want to. Wait a few more minutes and then we'll start the lecture. But in the meantime, you guys can sign in if you want. Annalise, can you check if the audio is working? Yeah. Can you go on the YouTube and check?
Yeah, it's good.
It's good? Okay, that's good.
No, we well, they do different. Oh, for chef. Oh wait, I don't understand chef. I understand about funny. Wait, chef. I know. I read the summary of chef, and then I'm like, oh, this basically all curly is fine. It's not. I'm gonna get chef. What do you think?
All right, we're gonna start the lecture. Today is ML Monday lecture number 8. We're gonna be lecturing on convolutional neural networks. And if you guys haven't yet, make sure to sign in using the QR code. We're also going to have the QR code at the end of the lecture. We'll get started. All right. If any of you guys are new, I'm Alvin Wong. I'm the Director of Education at GatorAI. And I have a few other ML lecturers who help me out sometimes with the other lectures. Kartik, Siobhan, and Shuniketh. And some of them are here today watching the lecture. All right. So let's do a recap of the previous lecture. Was there anyone here last week who kind of remembers a little bit about what we talked about? Does anybody want to say what they remember or kind of give an overview of the lecture? Yes.
Yeah, last week we were talking about training deep neural networks.
Yes.
A deep neural network is like a network with 2 or more layers.
Yes, that is good. Training deep neural network, where a deep neural network is a neural network with 2 or more hidden layers. Does anybody else want to add anything? Yes.
I know we generally don't like start the training like based on scratch, but like usually like it has some previous training.
Yeah, exactly. That's a good point. We don't usually start the training from scratch. Usually we have something called transfer learning, where we're taking a model and we usually take the first few or so layers that they've trained on a task, and we can kind of use it to fine-tune a different model that we want for our actual task. All right, anything else before I move on? All right, so that was a pretty good review. So as mentioned before by some of the other people, we talked about training deep neural networks, right? So we had the definition. A deep neural network is a neural network with 2 or more hidden layers. And most neural network architectures that are used today are considered deep, obviously. Some common ones would be like ResNet 18, which is a pretty popular one, or GPT-2. Those had 18 and 48 layers respectively, right? And a lot of the newer models today actually have hundreds, if not thousands, of layers that they use. So you can imagine how deep those neural networks are, kind of. All right, and we also talked about neurons. So this was something that was extremely important in understanding how a neural network works, right? A neuron is the single unit of computation in a neural network, right? And essentially what it does is it just takes in the previous input from the previous layer, or the inputs, it multiplies them by a vector of weights. And once we get this output, which is z, we use an activation function to finally get our final output, which we will pass to the future layer, right? And here we can represent this as a function, right? F w dot x plus b, and recall that w dot x is the dot product operation here, right? So w is, as I said before, our vector of weights, and x is the vector of inputs, right, that we're taking, and we just dot product them. And then if you guys don't remember what the dot product was, it's essentially just the summation of the weights and the inputs being multiplied together, xi times wi, right, from I equals 1 to I equals n is essentially what we're doing. And we can take anything to be our activation function that we want to get our final output y. For example, we can use the identity function f of z equals z, or the sigmoid function, which is given there. But we want our function to be non-linear. Does anybody remember why we want our activation function to be non-linear? Anybody at all? Yes, you in the back.
Because if it's linear, then they will just end up with a big linear regression.
Exactly, right? If we set our activation function to be a linear activation function, when we eventually add them all up together, it's just going to end up becoming just another big linear function, and linear functions don't usually represent a lot of things in the real world, right? And then also remember that neurons were loosely based on kind of neurological neurons, and the first kind of neuron that was created was the perceptron, right? And the perceptron was essentially a neuron with no bias, and it had a step activation function, right? So it just essentially, if the threshold for Z was past a certain amount, then it would just pass it itself. And this was created by Frank Rosenblatt, but nobody really uses perceptrons anymore because they did not perform very well. All right, so now that we've done a little bit of a review, let's move on to convolutional neural networks. So like regular neural networks, convolutional neural networks were also inspired in parts by kind of studies of the brain. There was two neuroscientists, Hubel and Wiesel, and they were experimenting on cats between the 1950s and the 1960s. And I think they actually got a Nobel Prize for their research. And essentially what they found when examining these cat brains was they had essentially electrodes that were recording the brain signals, and they would show a stimulus on a screen. And depending on what stimulus they found that they put on the screen, different parts of the brain of the cat would react. And so what they found actually was that the neurons had a very specific pattern, and they had a small, what we call local receptive field. And essentially what the local receptive field is that each part of a different, each neuron that was different in the visual cortex would respond to a specific part of the vision. So say, for example, you had a pixel that appeared in the bottom left corner, only a certain subset of the neurons in the cat's visual cortex would actually respond. So they found that neurons look at different places of the brain, right? And so that was kind of the inspiration of the convolutional neural network. And so essentially the definition of a convolutional neural network is just essentially a normal neural network, right, that utilizes convolutional layers that were inspired by this idea of the local receptive field in cat brains, right? And so we'll define a convolutional layer, right? It's a layer where each neuron processes information from a limited set of the previous neurons in the previous layer, right? So this is the idea of the local receptive field, right? Neurons do not take in every single output of the neurons in the previous layer. It only takes in a small subset as input, right? And that's kind of the idea here that was really used. And also, it's good to note that it actually took CNNs 30 years until like 1980s that they were able to be used for anything like super effective, and that they were able to be trained very well. So this kind of just shows like the idea of CNNs were around since like the 1950s, and but we really couldn't get them to work until the 1980s, and kind of shows how technology takes time to develop, especially stuff like this. So it's really interesting to think about here. All right, so we'll talk about convolutional layers, right? This is just a specific type of layer, right, that we said you can kind of implement into a neural network, right? And so a convolutional layer, right, is just, like we said, a layer where each neuron processes information from a limited set of the previous neurons in the previous layer, right? And so how it does this is essentially what it has is a set of filters. They're also known as kernels, or I'm going to call them filters just to kind of make it easier and simpler to understand, right? So essentially what happens is a filter is an array that slides or convolves across an image or the previous layer's output to produce a feature map, right? And so convolutional layers are usually used for image data, as you guys can imagine, because that's kind of the inspiration was that cats were looking at images, right? So we thought we could apply this to images as well, right? So I have a GIF here that kind of represents the convolution function, right? We have the input image, right? It's defined, it's like a width and height, and it has different values, which represent the pixels in this case, right? And so we have a filter, right, which is essentially an array, and it just slides across the input image, and essentially it just multiplies certain weights in the filter across the values of the pixels in the input image, right? And then you get your feature map. So you can kind of see how it slides across and it multiplies them all. And then you get the numbers in the feature map, right? And essentially what we're trying to learn in a convolutional layer is we're trying to learn the weights in the filter. And also there's usually a bias. So you'll add like just a specific number to every single number in the feature map, right? And then also we use an activation function on the final output of the feature map. So you can see in the feature map that it has -1 and -24, right? So usually we use ReLU as our activation function. ReLU, if you guys remember, is the activation function we used a lot in previous neural networks. So usually you would apply ReLU to the output of every single value in the feature map. So that -1, right, would become a 0, and that -24 would also become a 0 usually in the case where you're using an activation function, right? And so essentially when we apply the filter and we use a convolution, right, it produces a single output value for every single sliding window, right, that we have, and we get that feature map you can see here. Does anybody have any questions? Any of you guys have any questions, just feel free to raise your hand, and I'll get to you guys as soon as I can. Yes?
So the activation function in the kernel is not necessarily the same one that's used for the neural network?
It depends. You can choose a different activation function for your convolutional layer as compared to different layers in the rest of the neural network. So for example, you might use ReLU for your convolutional layer, but let's say your output, what your neural network is actually trying to do is classify the images. Maybe you would use you wouldn't use ReLU for your activation function, then you'd maybe use softmax or something like that for those classifications. So you can choose the activation function per layer that you want. Does that answer your question? All right, so now that we have the idea of the filter and kernel, let's go a bit more in depth. So in the previous GIF, we represented the filter as a 2D array essentially, right? And it just slid around the image pixels, right? The values of the image pixels to produce a feature map, right? But that's a good representation to kind of understand what's happening, but that's not actually how images are represented, right? Filters are usually 3D because their inputs are also three-dimensional, right? For example, most images today are usually colored, right? So usually the dimensions of an image will say, right, dimensions in quotations really, are commonly W times H, right, for the width and height, times 3 for the 3 main colors, RGB, that make up the color intensities of the pixels on the image, right? So we can kind of see on the top right image that normally our input isn't a 2D array, it's a 3D array. So in this example, right, we have the red, green, and the blue values, right? And so 6 by 6 by 3 matrix, right? That's the input for our convolutional layer, right? And then our filter is actually 3 by 3 by 3. It's a 3D kernel, right? And it's important to note, right, that no matter the dimensions of our input or the dimensions of our filter will always return a 2D feature map. That's kind of the most important part here, right? So the filters are usually 3D, but they'll always return a 2D feature map. And additionally, convolutional layers usually have multiple filters, and they will they'll output multiple feature maps, right? That kind of it uses as its output, right? So like we saw before, there was one filter that went across the entire image. Normally what you'll have something like 32 filters going across the image, right? And each of those filters will have different weights, a different bias, right? So that they can learn different features of the image. And so you can kind of see here how this all comes together, right? And like we said at the bottom, filters, they always return a 2D feature map no matter the shape of the filter, right? Also important to note is that the output of a convolutional layer will have shape of the width out times the height out times the number of filters or kernels that we're using, right? So let's say, for example, right, the top right image again, right? We have that 6 by 6 by 3 input image. Let's say we had 5 kernels, right? 5 kernels that are each 3 by 3 by 3, right? Then our output, we would have 5 feature maps, right? So we'd have 4 by 4 by 5 as our feature map data or bank, right? That's kind of what we say. So that's important to note, right? What the convolutional layer takes in as input, the dimensions, and then what it takes as output. Any questions? No. All right. So there are a lot of hyperparameters, right, that comes with this new convolutional layer. We talked about hyperparameters before. Does anybody want to give a quick definition of what a hyperparameter is? Anybody? Do you want to take a shot at it? You seem like you in the back. No? Carson?
A parameter that's set, like, or it's the tuning is set before you train. Is that what it was?
Yes.
Okay, yeah.
Is there anything else you want to add to that definition?
No.
No? Anybody else? You're halfway there. Does anybody else want to finish that? You in the back?
You modify them as you train to like optimize it.
Okay. I like that. Anything else? Does anybody want to? All right, no? Okay. The biggest thing, right, is that hyperparameters are not learned from the data, right? We choose them kind of our own accord, right? And it's up to us to kind of figure out what the best hyperparameters are. But the reason we don't learn the hyperparameters through the data is because that leads to overfitting, right? Because the hyperparameters actually have no relationship whatsoever to the data, right? That's the biggest part here. We don't want to learn the hyperparameters from the data, right? We do set them before, like Carson said, and the reason for that is because, right, we can't use the data to learn the hyperparameters. So let's go to hyperparameters of a convolutional layer. There's filter size, right? So we can choose different widths and heights for the filter that we're convolving around our image, right? For example, what was it in the previous GIF, right? We have a 3 by 3 kernel, right, as our width and height. So we can choose anything to be our width and height, right? And then the depth of the kernel, right, that third dimension is usually chosen automatically as just as the depth of the input it's given. And then we can also change the stride, as we call it. So this is the number of pixels the filter moves across the input image or right, its input each time it's applied. So you can see in the image that the stride is 2, so it'll jump 2 pixels to the right and then 2 pixels down, right? The next thing is the padding strategy. So the padding strategy, right, it's the technique of adding extra pixels, which are usually 0 valued, around the edge of the image before you apply the filter to the image, right? So you can see also in the image that we have padding of 1 and it's 0 valued right along the border. So that's how we can get the kernel to or the filter to have more pixels to look at, right? And finally, of course, like we said, we can change the activation function of the convolutional layer. The activation can be any activation function of our choice, but in most instances, it's ReLU because that's what's been found to work before, right? So those are usually the hyperparameters. And the two most important are stride and padding, which we're going to talk a little bit more in detail here, right? So for padding, right, like we said, it's the technique of adding extra pixels, which are usually 0 valued around the edge of the image before you apply the filter, right? So there's 3 main kinds of padding that we like to say. There's full padding, there's same padding, and there's valid padding. So full padding is you add extra padding so the filter can slide beyond the edges of the original input, and you can kind of see that in the image. Even if there's one value that the filter will touch in the input image, can add that padding to make sure that the filter can touch it, right? And we can kind of calculate the output size to be the input size plus the filter size minus 1, right? And that's with stride equals 1 as well. And then we have same padding, right? So same padding is essentially, we call it same padding because the feature map is the same dimension as the input, at least for width and height, right? So you can see same padding, we add 0 padding so that the output size equals the input stride, first stride if equals 1s, right? So output size equals the input size, and you can see that in the middle one, right, how it adds just a padding of 1, right, to make sure that the feature map is the same size as the input image. And then there's valid padding, which is just no padding at all, right? And the output size equals the input size minus the filter size plus 1, right? So that's how you can kind of see. I think the most important part here, right, is that the padding changes, right, the size of the feature map. And that's important because we want to know how many features we have and what exactly is happening in our convolutional layer, right? So we kind of have this idea that the padding changes the output, right, of the convolutional layer. And the next thing, right, is the stride. Like I said, it's the number of pixels the filter moves across the input each time it's applied, right? And so small strides are usually your stride is 1 in most convolutional layers, right? Because obviously it captures the most detail. If you have a large stride greater than 1, you're going to have coarser detail, right, in your feature map. But also it will require less computation, obviously, and also less memory usage. And that's kind of one of the biggest things, or one of the biggest reasons why sometimes somebody might decide to have a large stride, because you can imagine images can sometimes be like 1,000 by 1,000 pixels for width and height. And so that's a lot of information, right, that you're going to have to carry throughout your neural network. And especially also the filters, like we said, you might be using 32 filters, right, for your first convolutional layer. So then your second layer, the number, the size of your filter has to match the depth of that. So it have to be like 32 deep, right? And that you can kind of see how it builds up to be a lot of memory usage you're using in your CNNs, which is kind of one of the downsides, right? So that's one of the reasons why you might decide to have large stride. And so large strides, like I said, they're sometimes used for downsampling, right, which is like reducing the image width and height so that you don't have as much computation needed, and also the memory usage decreases a lot. And we can kind of see here, again, the same idea with padding, where if you change the stride, you're changing the size of your feature map, at least the width and height of the feature map, right? So you see if you have a stride of 1 and your input image is 5 by 5, then you're going to get a 3 by 3 feature map, right? But if you have a stride of 2, even with a 6 by 6 input image, you only get a 4 by 4 feature map, right? So this is kind of one of the things right here that's happening. So, we see all of this and we're saying, okay, maybe there is a formula at least so we can calculate the size of our feature map, right? And there is a general formula that we can use, right? Because it can be difficult to calculate the size of the feature map. And so the general equation, right, for h, which is the height, right, is h out equals h in minus the kernel height plus 2 times the padding for the height divided by the stride of the height, and then you floor it. That's what those brackets are, right? And then you add 1, right? And then it's the same formula essentially for the width, right? It's just using the width of the input image minus the kernel size of the width of the kernel, and then padding of the width, and then, of course, the stride of the width. Now, normally, your padding is the same for both your width and your height, and your stride is also the same for your width and your height. So normally, h out equals w out usually, right? I think there have been a few research papers that have tested between changing the strides for width and height, but as you can imagine, there's not much of a benefit to do that, really. And then also, most of the times, your h in equals your w in as well. Most of the time, your input images are going to be squares. And if your input image is usually not a square, what you'll do is you just kind of make a box around it so you can force the image to be a square, and you just kind of add 0 value pixels, right, or black pixels, so that you can just force the image to be square. And that's usually kind of what happens in CNNs. All right, so now we have our general formula to calculate the size of the feature map, at least the height and the width, right? And so the final thing to know about convolutional neural networks is a separate layer called the subsampling and pooling layer. This is a different layer from the convolutional layer. And the idea behind this is to purely reduce the number of dimensions of the feature map, right? Because the feature map can become quite big, right? The depth can grow very large, so we don't want the width and height to be very big as well, Because like I said, that's a lot of memory, a lot of computation that we have to use, right? So it's meant only for reducing the number of dimensions of the feature map. So it's a non-learnable layer, right? It's not learned. There's no weights or bias to learn. It's meant solely for dimensionality reduction, right? And we have a GIF here on the right-hand side that kind of shows two different techniques that are used in subsampling/pooling layers, right? We have this max pooling technique, right? Where essentially you just pass a filter around and you just take the highest value from the area covered by the kernel, right? So it's a very similar idea to a convolutional layer, right? Except we're not taking in, we're not using weights to multiply across the input image. All we're doing is using a very simple algorithm, right, to produce an output, right, for our next feature map, right? So that's max pooling, is just taking the maximum value out of the sliding window. And then we have average or mean pooling, right? And essentially all we do is just calculate the average between the area covered by the kernel, right? And you can kind of see how the features of the feature map differ from max pooling to average mean pooling, right? It's important to note that both of them are kind of used, but usually max pooling is the one that's used the most. I don't recall correctly what the actual reason is that max pooling is used over average/mean pooling. If I remember correctly, it has something to do with the fact that you want the most intense pixel value, because usually that's the information that has, that's a pixel that has the most information for that feature. If you're thinking about in terms of kind of how the different pixels come together to create patterns, right, that can classify an image or something like that. All right. So we've kind of gone through everything, right, about convolutional neural networks. So I want to kind of have a brief example of understanding, right, what a convolutional neural network does, right? So let's say you want to classify an input image into one of two outputs. Let's say you have images of cats and you have images of dogs, right? So what you do is you take the input, you pass it through your convolutional layer, right? Let's say in this example, you have 5 filters in your first convolutional layer, right? Since you have 5 filters in your first convolutional layer, right, you have 5 feature maps that you are going to create, right? So that's kind of, right, the feature extraction here is that it's happening, right? So once you have your 5 filters and you get your 5 feature maps, what you're going to do is you're going to stack them. So let's say the input image was 32 by 32 pixels, right? And then let's say we have a filter, right, that has stride of 1 and padding of 1. So essentially, that's just same padding, right? And then we have 5 kernels. Does anybody know what the dimensions of the feature maps, the feature map bank would be? Does anybody know? It was 32 by 32. And we use 5 filters. We have same padding. What would be the dimensions of the feature map bank? You look like you're thinking hard. You know? What is, you want to?
I don't know.
You don't know? Anybody? You in the back?
Is it 32 by 32? By 5.
Yes, it's 32 by 32 by 5, right? Because we have we have same padding, right? And stride equals 1. So the feature map has the same dimensions as the input image. And since we have 5 kernels or 5 filters, then we have 5 feature maps, right? So the depth is 5. And then the input and the width and the height would be the same, right? So then normally what happens after you have a convolutional layer is you use your pooling layer, right? Or the subsampling layer that we talked about before. So right, in this example, something that might happen, right, is you would just reduce it by you would use a filter size of 2 and you'd use max pooling, right? And so you can kind of see how that reduces the size of the feature maps, right? And then after we have those reduced sizes of the feature maps, all essentially we do is we just flatten the feature maps together. So we have a bunch of 2D arrays. We just flatten them into one ginormous 1D array. It doesn't really matter how you flatten the feature maps. all that it matters is that every single time you flatten the feature maps, you flatten them in the exact same way so that the neural network knows exactly kind of what you're passing in and can learn the relationships. So, and then once you flatten all of the feature maps, essentially what you're left with is what you normally pass into a singular feed-forward neural network, right? So it's just a fully connected neural network. You pass it through, and then you have your output at the end, right? And so like a normal feed-forward neural network, you're going to use propagation and gradient descent to update the weights of your normal neural network, and then that will update eventually the weights of your kernel, right? The bias of your kernel, or your filters, right, across the convolutional layer. So that's kind of the idea of a convolutional neural network. And kind of one of the most important things, right, about the convolutional layer is that it can kind of learn different features and how the pixels interact together, right? Because essentially what's happening is that the different filters, because they go across the image, they can kind of learn how pixels come together. So maybe one, filter might check if there's certain edges, if there's a straight edge in a certain area of the picture. Another kernel might check if there's like a diagonal edge or something like that. So essentially, the intuition here is that each filter will learn different that can be present in an image, and it checks if those features are at different parts of the image. And that's why convolutional neural networks are so good at finding used for image classification and stuff like that. All right, so we're going to have, this is going to be a bigger example, right? And so hopefully this helps you guys understand exactly what's going on and how the filter size changes and how the input size changes, right? So we have our input image right here. Here, this is 224 by 224, and we have 3 color channels, right? So our width is 224, our height is 224, and our depth is 3. That is the input, right? So it's a 3-dimensional matrix, 3-dimensional array, right? Classic. So we're going to pass it to our first convolutional layer, right? So our first filter shape is going to be 3 by 3 by 3, right? So the first 2 3s represent the width and the height, and then the third 3, right, represents the depth. And then we're going to have 64 filters, right? 64 filters. Each filter is 3 by 3 by 3, right? That is its dimensions, right? And we're going to be using stride equals 1, padding equals 1, right? So it's the same padding strategy, right? And essentially what we get, right, is we get as output from our first convolutional layer, it's at the bottom, right? So the input is at the top, or the filter size is at the top, and then the output size is at the bottom. So we get 224 by 224 by 64. That is the output size, right? It's what the first convolutional layer block is outputting out, right, as an array, essentially, right? So once we have this 3-dimensional array from our first convolutional layer, it's a bit too big, right? So we're going to use the subsampling or the pooling layer, right, that we discussed before to reduce the size of this output, right, this 224 by 224 by 64 dimensional matrix, right? So we reduce it in half, right? We reduce the width and the height by half. So that way we get 112 by 112 as our width and height, right? But remember, we still have those 64 kernels, or those that depth of 64, right? So then the filter for our second convolutional layer block is 3 by 3 again for the width and the height, but the depth needs to match the depth of the input, right? So the input of the second convolutional layer is just the output of the first convolutional layer, right? So since the output of the first convolutional layer has dimension 224 by 64, and we have to match the depth, we have to have our filter match the depth as well. So our second filter shape will be 3 by 3 for the width and height again, and then 64 for the depth, right? And our second convolutional layer has even more filters. We have 128 filters, right? So that's why at the very end, we get 112 by 112 by 128 as the output for the second convolutional layer block, right? It's passing this all along every single time in one go. right? And then finally, we have the third filter shape. As you can imagine, it's the same thing as before. We use max pooling to once again reduce the width and the height by a factor of 2. And then since the input depth is 128, our filter's depth also has to be 128 in this case, right? And we have 256 filters. And so it kind of just goes on, and eventually we get enough to where we can flatten the output of the fifth convolutional layer block, right? And then we just flatten it into a single one-dimensional array, and we pass it through our feed-forward neural network, right, for classification. And so that's kind of the idea of the convolutional neural network and how all the information passes along it. And you can kind of see how it works. So intuitively, what's really happening, like I said before, is that the depth, right, of the feature maps, or each feature map represents kind of a feature in the image, right? So maybe, and there's 64 feature maps in the first convolutional layer, we capture 64 features that might be present in the image, whether they be edges or colors or how certain colors come together. And then in the second convolutional block, we have maybe 128 features that we can kind of come together and figure out what's going on, and so on and so forth. You can kind of see the funnel architecture here at work too, that we discussed in previous neural networks, how you kind of want to have very, very large layers at the start, and you kind of want to narrow it down as you go forward to kind of get those features. And then finally, we can just pass it through our feed-forward neural network, right? Are there any questions so far? All right. Yes. So that's basically the end of the lecture today. It was a bit of a short lecture. That's all right. The main takeaways, I would say, right, there's a kind of a lot of information to cover, was that convolutional neural networks is essentially just a feed-forward neural network, right, that utilizes layers called convolutional layers, right? And a convolutional layer is just a specific layer that you input into a neural network where each neuron only processes information from a limited set of neurons from the previous layer, right, through the usage of filters, right, and doesn't take in as input the entire previous layer. That mostly happens in normal feed-forward neural networks, right? So a convolutional layer, right, it will take in an input of shape Win times Win, right, times Dn, right, where the Dn is essentially the number of colors from the input image, or it is the number of feature maps from the previous layer, right? That's what the depth represents here, right? And a convolutional layer will always produce an output of Wout by Hout by Dout, right? Where Wout and Hout, like we said, are determined by the hyperparameters of stride and padding, right? And the depth out, right, is determined by the number of kernels that we have chosen for the convolutional layer, all right? So that's kind of the input-output and seeing what's going on there, right? And then finally, right, we talked about the kind of the filter and the kernel, which is based on the idea of the local receptive area, right, that was found from cats. And, right, the filter is just an array that slides or convolves around the image or the previous layer's output, and it always produces a 2D feature map, right? So I think that concludes our lecture today for convolutional neural networks. If you guys haven't already, make sure to sign in. And also, if you guys have any questions, feel free to come up and ask me anything. I think that will be it for today's lecture, though. Thank you.